All right. The required humorous introductory slide. Some of you might be married, and this may look slightly familiar, but this is a continental perspective on marriage. Well, looking back, I guess it had been going on for quite some time, but I only noticed we were drifting apart the last 50 million years. So, all right. So the idea that the continents drifted is something that started to appear as soon as we had pretty good maps of the world. And this is Ortelius's Theater of the Lands of the World in 1570. And the continents are recognizable even if the Americas are slightly different. And if that land, Australia, is I'm sorry, Antarctica is a little bit larger than it is. It is recognizable. So Abraham Ortelius was, a cartographer, 1527 to 1598. That lived to be an old man for those times, 71 years. This is considered to be the first modern map of the world. And so let's read this. This is also likely owing to the fact that the coasts of certain lands situated opposite each other's, though separated by sea, have a corresponding shape so that they would be congruent with one another were they to stand side by side. For example, the southern part of America and Africa. For this reason, one supposes that perhaps both of these continents were previously attached to each other, either directly or through the sunken island of Atlantis, just as Sicily was attached to Naples, Ceylon to the mainland of India, Sumatra to Malacca, Britain to France, and so on. So that's kind of remarkable, just looking at these really crude maps. And that story of Africa and South America looking like they once were together continues. We'll see it over and over again. So the similarity of South American and African coastlines has stimulated imagination for some time. So this is considerably later. This is 1858. Schneider Pellegrini made these two maps. They depict his interpretation of how the American and African continents may once have fit together before subsequently being separated. Avant la separation, before the separation, after the separation, today. Now, about this, in the late 19th century, Swiss, Austrian paleontologist Edward Suess, who lived to be ripe old age, started talking about the southern continents being together at one time. And this is where the word Gondwana land comes from. This is Suess's name. We'll hear this name again and again. And what you can see is, I think you can recognize all of the names of the oceans, the Pacific. The Atlantic is kind of closed there. And then there's this sea called the Tethys going east-west between North America and Asia and this southern continent that he called Gondwana land. Okay, so he proposed Gondwana land in 1885 because of the geological correlations he saw. He's also the person that coined the name biosphere, which is now a big term. Now, this is a fellow who doesn't get much credit, Frank Bursley Taylor, American geologist. He was actually a glaciologist. And in 1908, he gave a talk to the Geologic Society of America, and he proposed continental drift as a mechanism for the origin of mountain belts. So Taylor's oral presentation was 4 years before Alfred Wegener's book, and his publication was 5 years before Wegener's. And sometimes we'll call the continental drift hypothesis the Taylor-Wegener hypothesis. So in his 1910 paper in GSA Bulletin, he said the Mid-Atlantic Ridge was a place where he didn't call them plates, but where the separation occurred. And the Himalayas was a place where the Asian continent was being thrust out over the Indian crust. Very similar to what we're going to see later in this class, only the difference is that it's India being subducted beneath Asia, Asia being relatively fixed. Likewise, the Aleutians were being thrust out onto the Pacific Ocean floor. In a later paper, he proposed that this occurred by continents being dragged towards the equator by tidal forces as a result of the hypothesized capture of the moon, resulting in a general crustal creep towards the equator. Now, that's not the origin of the moon as we understand it, but I think you start to see through these different takes on a similar thing that the science is advancing, even though at every stage we can see mistakes, things that we would say, okay, that's wrong. And that's very common in science. If we're making progress, we're making a little bit of progress, we're still making some mistakes. This was his map. So here you can see he's emphasizing the southward motion of Asia, the westward motion of North America, which is happening, and the westward motion of South America, which is happening. So it's starting to look like a very modern looking map. Now, then Wegener comes along. He was short-lived, only lived to be a 50-year-old man. He was a climatologist and a geophysicist who proposed that the single continent, which he called Pangea, existed in the past and broke up about 200 million years ago. And then these pieces then drifted to their present locations. This is just the geologist observing and explaining, but the geophysicists obviously had problems because they knew the mantle was solid and it was unimaginable that solids could flow like that. So in 1915, very bad year for a German paper. The first of his works, The Origin of the Continents and Oceans, his brother remarked that his motivation was to reestablish, quote, reestablish the connection between geophysics, geography, and geology, which had ruptured because of the specialized development of these branches of science. Now, that's more than 100 years ago, and those fields have only become more specialized. So, but nevertheless, these things that we'll be talking about, continental drift, seafloor spreading, plate tectonics, these do unite these different disciplines, especially geology and geophysics, which always have this tension between them. The US scientists in particular opposed his idea. Now you can say, well, it was partly because it was a German idea, so nobody liked Germany. No, the United States didn't like Germany. Maybe that was part of it. Who knows? But anyway, the American Association of Petroleum Geologists organized a symposium in the 1920s, specifically in opposition to the continental drift hypothesis. And the opponents argued that the oceanic crust was too firm for the continents to simply plow through it. And they were right. That's not how it happened, but they had no idea of what actually made the plates move apart. But this map showing the geologic, really the paleontological arguments for a single supercontinent. This looks like Gondwana land, right? The southern supercontinent. You know, we've got four things on here. We've got in orange the fossil remains of Scicomm, a Triassic land reptile, which is in both Africa and South America. We've got fossil evidence of a Triassic land reptile, Listosaurus. We've got a freshwater reptile, Mesosaurus, in both Africa and South America. And then we have this very diagnostic tree fern called Glossopteris, very characteristic fauna of the southern supercontinent. And Clint's got a question.
Yes, more of a comment that the geologists in South Africa, South America, India, and Australia were very early on convinced of the connection between these continents in some way. Sometimes it was the continents were together, other times they devised land bridges, but they were A-okay with the idea of them being together because they had the rocks. They lived on the rocks.
And more importantly, they had the fossils. This argument is, as you can see, is largely paleontological. Okay. All right. Now we're gonna talk a little bit about Euler. So we'll talk about the Euler poles later in this class. The Euler theorem. He's not a geologist; he's a mathematician. He was also back then in this early 18th century. You could be a mathematician, a physicist, an astronomer, a logician, and an engineer at the same time. And he made many contributions. And introduced a lot of modern mathematical terminology and notation. And Laplace emphasizes the importance of Euler. Read Euler, he's the master of us all. So what the Euler pole is basically an imaginary pole on any sphere. And basically it says that the motions of any two plates or any two surfaces that are moving independently on a sphere can be described by an angular velocity around a common pole of rotation. Now, that pole of rotation is not the Earth's rotation axis. It is a theoretical pole that is simply a device to explain the relative motions. Okay, and we'll talk more about this when we get into plate tectonics. So again, this is his representation in mathematics. In 3D space, any motion of a rigid body such that one point or stays fixed is equivalent to a single rotation about an axis that runs through the fixed point. It also requires that the motions of any two rigid bodies can be described as a rotation. The axis of rotation, or the pole of rotation, is sometimes referred to as an Euler pole. And we'll use those terms interchangeably later in this course. So, computers come along, geophysicists are using computers, and a very famous geophysicist, Edward Bullard, used as one of the early ones, what does that look like, 60 years ago? To do a computer fit of the coastlines of the continents around the Atlantic. And what he finds is they fit extremely well with a little bit of overlap, shown there in black. This fit is to the 200-meter isobath, that is depth, right, the edge of the continental shelf. And so the geophysicists now are starting to get more interested in these ideas. He doesn't have an explanation, but he's saying, man, that is not only an interesting fit, that is a tight fit. That is it'd be very difficult to make that coincidental. So this is 1965. Things are starting to move. Now, we have to keep in mind that much of the continental crust is submerged as continental shelf. So when we talk about continental crust, we're usually thinking about the continents, but here we see a good example, the Bering Continental Shelf. That's a huge, broad area. And so even though it's below sea level, we still have to treat it as if it's continent. There's going to be more and less shelf exposed depending on whether sea level is rising or falling. So this is about 30% of the continental crust lies below sea level as continental shelf. Here's a good example. So if you're going to close the continents around, say, the Atlantic, you don't take it coastline to coastline. You have to take it out to the edge of the continental shelf. The extension, and we'll talk more about how the transition occurs between continental crust and oceanic crust. We haven't talked about that yet, but we will. Now, there's some problems with this fit, and one of them is Mexico. So if we close these continents, South America against Africa, North America against Africa, Europe, there's no place for Mexico, which points out some very interesting problems. And this is one way that people have resolved this. This is the Yucatan sort of being snuck in there, the Chortese block, which is basically Honduras now. So somehow that rotated out of there during the opening of the Gulf of Mexico. Oops. Yes, we'll still call it the Gulf of Mexico. Another one is the Bay of Biscay, here between Spain and France. This region in here opened like this. Iberian Peninsula rotated against France like this. So that's another one of these problems that has to be dealt with. But by and large, the Bullard fit is doesn't require too many of these adjustments. Now, one of the things that we notice is that when you bring these continents back together, this brings some old suture zones together. So this is an orogenic belt. We talked a little bit about orogenes and orogenic belts last lecture. And there's actually two of them in here. One of them is an older one. It's called the Caledonian in Europe and the Tectonic in North America, early Paleozoic, about 400 or 500 million years ago. And this other one is a late Paleozoic one called the Hercynian or Variscan, the stipple pattern, which can be traced into here. And these orogenic belts line up when you close the oceans. Another thing that lines up are cratons and younger mobile belts. So when we say mobile belt, think orogeny or orogenic belt. But we've talked about cratons, and here we've got the West African craton, the Amazonian craton, the Congo craton, a little piece of which lies in Brazil, and the Kalahari craton. So the cratons kind of line up if we close them back together. So it's not just the coastlines, but other geologic features. Remember, Wegener was looking at solving some problems in paleontology by closing the ocean. But with more recent work in the 1960s, people noticed that if we close these oceans, the Atlantic Ocean, it brings together geologic provinces of similar age. So it's like, this is just getting more and more convincing that that's what happened, even if we don't understand why it happened or what caused it. Here's another example. So one of the things that is characteristic of especially southern Gondwana are these Mesozoic flood basalts. So flood basalts we'll talk about later. They're associated with mantle plumes. What happens when the mantle plume reaches the surface? You get this huge outpouring of basalt. And so these Mesozoic flood basalts of similar age are found. We don't really, most of Antarctica is covered in ice, so we only see a few places where it's exposed. But it lines up very nicely with the Karoo flood basalt province of South America and the Piranha basalts of South America, South Africa, and South America. Then we have some very interesting rocks called anorthosites. These are unusual igneous rocks composed almost entirely of plagioclase. They're very common in the Mesoproterozoic, about 1 billion to 1.6 billion years old. And this region of anorthosites lines up very nicely if you put them back together. And then the other interesting thing is the limit of the Permo-Carboniferous glaciation, the late Paleozoic glaciation. The limits of that looks like this if you put the continents back together. And if you say that didn't happen, then what you've got is a glaciation coming from the south in tropical India. So that is a very difficult thing to explain. But it's very nicely explained if we take Seuss's Gondwana configuration and plot these things on it. So it's getting pretty convincing, huh? All right, so back to the supercontinent Gondwana, Edward Seuss. This configuration existed until the Jurassic time, and then it started to break up. And the name Gondwana, it's kind of an interesting name. It comes from, Seuss named it after the Gondwana region of northern India, Sanskrit Gondwana, the forest of the Gonds, from which the Gondwana sedimentary sequences, Permo-Triassic, are also described. So these are the correlation of Paleozoic, early Mesozoic sediments across the former pieces of Gondwana. So here we're going from the Carboniferous, which would be the Mississippian and the Pennsylvanian in the United States, the Permian, the Triassic, and the Jurassic. And then we're looking at the very simplified lithologies in Antarctica, South Africa, South America, and India. And what we see is remarkable similarity with, there's some differences over a scale like this. But here we have the tillite, the evidence of the late Carboniferous or Pennsylvanian glaciation, right? Over all of these southern continents. We saw that here, right? That's the limit of the Permo-Carboniferous glaciation. Then we've got the shales, and that contains our freshwater fossil Mesosaurus. Then we have coal measures, right? The coal of, in the northern hemisphere, the coal is Carboniferous. That's why we get the name. But in the southern hemisphere, the Paleozoic coal is mostly Permian because it was glacial in the Carboniferous, and it had to warm up so the trees could grow in order to make coal. And Triassic, a lot of sandstone. And then the Jurassic is when we get these basalts. The Farrar basalts in Antarctica, the Karoo basalts in South Africa, the similar basalt in Brazil and in India. So the sedimentary sequences line up very nicely. Here we see the fundamental problem for those who denied continental drift happened. We can use the glacial striations to indicate the direction of ice flow, right? So here's the limit of the ice. Here's the scratch marks showing the direction. And in India, it looks like the ice came from the equator and flowed north. This causes a tremendous problem for anybody who wants to argue against India having migrated north from the South Pole region. All right, now, if we're going to make a paleoclimatic argument for continental reconstructions, the reassembled continents should be consistent with the climate evidence preserved in the sediments. For example, carbonates and reef typically form at low latitudes, today within about 30 degrees of the paleo equator, usually even closer. So that reconstruction should have whatever carbonates and reefs that are found forming at low latitudes. Evaporites today mostly form between 10 and 50 degrees north and south of the equator. Red beds, these are very iron-rich sandstones. These continental sandstones form within 30 degrees of the equator. Coal, that forms in tropical rainforests or temperate forests. Phosphorite is a very interesting one. This is, deposits made out of phosphate, very important for agriculture, fertilizer. These form within 45 degrees of the equator along the western margins of continents or at low latitudes along east-west seaways. Bauxite and laterite, these are very weathered soils. Bauxite is an aluminum ore. Basically, you weather soil and all that's left is the aluminum oxide. Laterite is slightly less weathered. It contains the iron too. These are ultra leach soils requiring tropical or subtropical weathering. Desert deposits, they can form at high or low latitudes, but dune deposits should give reasonable wind directions. And glacial deposits, of course, these generally form at high latitudes. All right. Now, we've talked about the supercontinent, the Paleozoic supercontinent Gondwana. There's another one in the north. This is called the combination of Laurentia, the old, before North America became North America, which happened after it separated from Africa and South America. It was called, we call it Laurentia. And Laurentia is basically, with the exception of Florida and some of the Appalachian Piedmont, Laurentia is basically North America. But it was combined with Baltica, which is the Baltic region over here, Scandinavia today, and northwest Russia. This is called Laurussia. Now, sometimes people call it Laurasia, but in fact, Eastern Asia did not form until later. So the northern supercontinent, which isn't nearly as famous as Gondwana land, I had a sticker on my back of my car said "Reunite Gondwana land" that elicited some curious people couldn't figure out whose side I was on. But this is the northern supercontinent. This is in the early Paleozoic, 420 million years ago. All right, so this continent, southern continent, Gondwana, and the northern continent, Laurussia, collided in the late Paleozoic to form the Ouachita, Appalachian, Variscan origin, and the supercontinent Pangea, right? So there's two supercontinents are in this supercontinent called Pangea. So, Wegener didn't really understand this. He didn't need to. So here we see Pangea sort of in a end Paleozoic configuration. And between the two, where the collision happened, is an orogenic belt. We talked about that as the Caledonides and the Variscides. These are basically the Paleozoic origins led to this. Between the northern supercontinent and the southern supercontinent, in the east was the Tethys. We've mentioned Tethys before, and in fact, there's several iterations of Tethys. It's an interesting topic if somebody wanted to take, that as a research topic, because there's a Paleotethys, there's a Mesotethys, there's a Neotethys, and in fact, there's a Paratethys. And then what is now the Pacific Ocean is the world, if there's going to be one supercontinent, there's going to be one super ocean. So this is called Panthalassa, So that's kind of a late Paleozoic configuration. All right. So as Pangea deposits are very consistent with the expected climate zones. So here we've reconstructed Pangea as a single supercontinent. And what we can see here are the areas of glaciation between 300 and 250 million years ago. That is sort of in the Pennsylvanian and the Permian. They're all here. This is under ice still, so we imagine that these evidences of glaciation are there. So you can see this glacial cap is sort of focused on the southern pole. Now, this is interesting. This is the areas of tropical coal forests at 300 million years, the Carboniferous, right? The Carboniferous was critical for the Industrial Revolution. The coal deposits of England started it. There were coal deposits of similar age in Germany and in the United States, in the eastern United States. And this remarkable energy source for the 19th century industrialization is a gift of the Pangea, of the formation of Pangea from the collision. All right. So paleontological evidence, just as today, plants and animals evolved differently in different parts of the world. So their mountains, oceans, and deserts, as well as different climate zones, acted as barriers that kept different populations isolated. And if we reconstruct the continents, we should bring similar flora and fauna back into proximity in a way that is consistent with the presence of or absence of barriers. Those barriers obviously are different for aquatic creatures than it is for land creatures, right? An ocean is no barrier to a fish, but is to a horse, and vice versa. So at all times, the biodiversity, that is the number of species and genera, should increase towards the equator. And decrease towards the pole. Life is harder where it's colder. Life is easier where it's warmer and wetter. So one of the interesting things that developed relatively early, 1970s, was this recognition that there was more diversity when the continents were separated than when they were together. So this is going from the Cambrian, right, about 500 million years ago, until the Cenozoic, right, today, we're right here. And obviously the Phanerozoic life, especially the marine fossils, the invertebrate fossils that this is based on, they were, first thing is they're taking off here, right? The appearance of visible fossils begins in the Cambrian. There's some finer things that have been found in slightly earlier times, but the recognition of easily identified fossils begins with remains in Cambrian and younger rocks. And what you can see is the number of families, right? This is the way paleontologists measure diversity, right? More families, that's more diversity. Fewer families, that's less diversity. And obviously at the beginning, there's going to be less diversity than later. But here we're looking at a simplified fragmentation of the continents. So here we've got a single supercontinent at A, also one here at E, that's Pangea. And then Pangea breaks up and we have the present configuration. And what you see is as we go through this sequence from one supercontinent to another supercontinent, we go through this fragmentation and amalgamation phase, and the diversity of fossils, as preserved in the fossil record, the diversity of animals as invertebrate marine animals, increases as we go to more fragmented and decreases as we go to a supercontinent. And this makes sense because evolution basically is a reflection of isolation, because isolation allows inbreeding and the development of certain traits. And so we see this increase in diversity with continental fragmentation, and then decrease with continental amalgamation, and then increase again. And we're going to talk about the supercontinent cycle. And what you don't see here is this is one supercontinent. This is the second supercontinent. This is how long it takes to go through one supercontinent cycle, at least one. That's on the order of about 300 million years. And we'll talk more about the supercontinent cycle at the end of this class. All right, so we saw this. Here let's take a little bit closer look at the fossil remains of Mesosaurus. So that's reconstructed Mesosaurus, an early Permian reptile found on Gondwana and continental fragments. It was a freshwater aquatic reptile, so it couldn't swim across the Atlantic. So reasonable thing to ask would be, how could the same creature live in what are now far separated continents? Obviously, if they were originally together, it'd be no problem for them to swim. Now let's look at Glossopteris. Glossopteris was a giant Permian seed fern, and it lived in Gondwana. And here's a leaf impression of Glossopteris. These plants became dominant part of the southern flora, but they were extinct by the end of the Triassic. And evidence of the Glossopteris fauna is only seen in the southern hemisphere, only in the Gondwanan continents, not in the northern Laurentian supercontinent. So we have these distinct Permo-Triassic floras and faunas in the southern and the northern, right? Gondwana and Laurussia. The southern biota was strongly affected by the nearby ice sheet, but the northern biota was not, right? So down here we see sort of a polar Gondwanan flora with few species. I don't know what Eurytisma is. These are Tethys marine foraminifera. Foraminifera are single-celled organisms, and you can find them in a belt that can be extended across there, basically evidence of this Paleotethys. And then the tropical Laurentian, here it's called Laurasian, flora with many species and areas of identical reforming corals, followed later by tropical cold forests. So cold forming forests like that. These belts line up very nicely in this Paleozoic reconstruction. Now, about this time, people started getting interested in studying Earth's magnetic field through time. This is the field of paleomagnetism. So here we see Earth's magnetic field, right? Earth's magnetic field can be simplified to a dipole, right? A bar magnet. Obviously, it's more complicated than that, but basically with one end being the magnetic North Pole and the other one being the magnetic South Pole. In fact, the geographic North Pole, the pole of rotation, is not too far from the magnetic North Pole. Magnetic North Pole and the geographic North Pole are a bit different, but right now they're fairly close. To all intents and purposes, they're the same. And this magnetic field is acquired by some kinds of rocks during their time of formation. So the minerals that capture this magnetic field are ferromagnetic minerals, and magnetite is a very good example of one. And these will capture two things of interest to paleomagneticians. One is the magnetic declination. That is the angle that a compass needle makes with the line running to the geographic North Pole. And the other is the inclination, and that's the dip of the magnetic field. So that dip is horizontal at the equator. You can see the magnetic lines, force lines are basically parallel to the Earth's surface at the equator, and they're almost vertical at the poles. And if these rocks will lock in these magnetic declinations and inclinations, these can be later used to determine paleolatitude, but not paleolongitude. We don't know where at a given latitude a rock might have formed. We can, with some relatively straightforward assumptions, identify its paleolatitude, but not its paleolongitude. And it can also be used to determine the rotation relative to magnetic north. Right? So, Clint, you had a question?
No, just make sure you get those L words right.
What whale words are those?
Latitude and longitude.
Did I say them incorrectly?
We can determine latitude. We can't determine longitude.
That is correct. All right, so there's many kinds of magnetization preserved in rocks, but these can be basically summarized under the the name natural remnant magnetization, or NRM, which can be primary, that is, it formed when the rock did, or it could be secondary. It could form after the rock as a result of alteration. So primary NRM, that there are two types of that. The first one is called thermoremnant magnetization, which is acquired when rocks cool below what's called the Curie temperature, which is when magnetite and related minerals lock in the magnetic field that they're sensing. And it's about 600 degrees centigrade. So igneous rocks erupt at something close to 1200 degrees centigrade, but it doesn't take them long to cool down to 600, a few days, a few weeks, maybe a month. And at that time, whatever the magnetic field will be acquired by the magnetites as thermal remnant magnetization. In clastic rocks, you can also get a detrital remnant magnetization, where what happens is the transported grains of magnetite, they're not heated to 600 degrees, so they don't acquire the magnetic field, but they maybe subtly align with the magnetic field when they're deposited. So that is another kind of magnetization that paleomagneticians study. Now, the problem with paleomagnetism is secondary NRM, which is acquired later, and it can be useful if you know when it was acquired. So there's chemical remnant magnetization, which happens when a ferromagnetic mineral forms as a result of chemical reactions, for example, as a result of diagenesis, alteration, or metamorphism. There's isothermal remnant magnetization. That happens when rocks become magnetized by a very strong magnetic field, for example, during a lightning strike, right? High mountains are very subject to lightning strikes. So paleomagneticians avoid peaks when they're collecting their samples. And then there's viscous remnant magnetization, which occurs when a rock remains in a relatively weak magnetic field over a very long period of time, slowly acquires a new magnetization. Primary NRM is very useful for testing continental drift. Secondary NRM is not. And you have to be very careful to distinguish these two things. Any questions about that? It's complicated, but really quite interesting for those that are interested in it.
I'm just curious, when a lightning strikes, does that really impact a very big area, or is it pretty small?
Pretty small. I don't know what the area is, but the fact of the matter is that mountain peaks get lots and lots of lightning strikes. So, you're just lightning strike on top of lightning strike. But yeah, it's kind of an interesting, geo trivia fact. I've always wanted to start a game of Geo Jeopardy, with contestants, but it hasn't happened yet. All right, so let's talk about NRM.
Don't take metamorphics for 400.
So natural remnant magnetization can be primary, formed when the rock did, or secondary, formed after the rock. We just talked about that. Primary NRM of igneous rocks is thermal remnant magnetization, as we said, acquired when the rock cools below the Curie temperature. I said 600, 580 is correct, close enough. So here's Earth's magnetic field, and here we've got, a microscopic image of an igneous rock with lots of magnetite grains. So here we're looking at what's being locked into the magnetites in terms of the magnetic field. And you can see that they're all different directions at temperatures greater than the Curie temperature. But at below the Curie temperature, those magnetite grains lock in the magnetic field and they preserve it. So the igneous thermal remnant magnetization is much more reliable in quickly chilled lavas than in slowly cooled plutonic rocks. So paleomagneticians learned early on to concentrate their work on basalt lavas, not granites. This is a representation of detrital remnant magnetization. So here we got water, some unconsolidated sediment, and here's some consolidated sediment. And these are the magnetic force lines. And these are sort of the orientations of magnetite grains and, how they align with the magnetic field, or how that's thought that happens. All right, so isolating the primary magnetization, TRM, DRM, and CRM are hard magnetizations. Whereas VRM tends to be soft. So when they would measure the rock magnetization, you have to remove these VRMs and other soft components of magnetization to get at what was created, the magnetization that existed at the time that the rock formed. All right. So Earth's magnetic field is presently a dipole, inclined 11 degrees to the rotation axis. Like I said, it's very close to the rotation axis. This is probably a result of convection in the liquid outer core. The dipole axis rotates around the pole of rotation, migrates. You might see some of this stuff in different social media talking about how the Earth's magnetic pole is moving. It's always moving. If a paleomagnetic study of a rock sequence indicates a magnetic pole location different than that of today, either the pole has moved or the rock has moved. Assuming that Earth's always had a dipole. Paleomagnetic reconstructions assume that the Earth's magnetic field has been a dipole through geologic time. And with this key assumption, the magnetic inclination could be used to determine paleolatitude, again, but not paleolongitude. And the declination can be used to determine if the block is rotated relative to magnetic north. So here's an example. Consider a rock with a good thermal remnant magnetization. This is oriented 25 degrees east of due north. That's the declination, and dips 40 degrees to the northeast. So what can you say about what has happened to the rock since it passed through the Curie temperature? Does anybody want to take a guess?
Would that be uplift?
Well, more specifically, there's two lines of evidence in this measurement. One of them is the fact that the TRM is oriented 25 degrees to the east of due north. That's its declination. And it dips 40 degrees to the northeast. That's its inclination. Can you say anything about how this parcel of rock has been, where it formed or how much it's rotated?
I would say it's moved by about 15 degrees, rotated as well as shifted north.
Well, let's see. If it dips 40 degrees to the northeast, then what latitude did it form at? Remember, it's the inclination is horizontal at the equator and
15
No,
degrees latitude.
It formed at 40 degrees north or south, right? Because that's the inclination tells you the latitude. The rotation of 25 degrees to the east suggests that the rock has been rotated 25 degrees clockwise. You see it? No? Is that, if you're confused, please articulate why you're confused.
Would you also have to age the rock to be able to?
Yes. You have to have some constraint on its age. But this is not, we don't need to talk about that.
Oh, okay, okay.
Just with this measurement of the paleomagnetics of this rock, you can say this rock has been rotated 25 degrees clockwise, and not just the rock, because the rock is, Clint's got you want to comment, Clint?
Just that I put in chat a link to a simulator from the university in Lyon, France, where you can take a rock of a certain age with a inclination and declination, and then try to match it up with what the magnetic field was like then, and then see if you were right. So they have several things, including Euler poles, which you can look at. Also, some short videos that are short and to the point.
Okay, thank you.
But this wouldn't, well, I guess age again would consider the help, but as far as it's lining up that, like precession and everything else with the rotation, and then a wandering pole, pole reversals, I guess knowing its age is what would help you line up where it might have been at that time?
Well, we don't know how the Earth's magnetic poles have migrated. The assumption is that they have migrated, but fairly closely to the geographic north and south poles. So the declination and the inclination are considered to be relative to geographic north, even though we know that's off by a few percent or maybe 10%. But still, with that assumption and the errors that implies, you can say that this block, whatever you got the rock from, has rotated about 25 degrees clockwise relative to north, because it's showing north to be in a direction that's not north, and that it formed at about 40 degrees latitude because its inclination is capturing that. I mean, this is very much simplified paleomagnetism, but that's what you can get out of rocks if you have good data. All right, so when the paleomagneticians started collecting data, they saw a problem, and let's look at this diagram on the left here. So here we're looking at the apparent polar wander. So right now, the magnetic pole and the geographic pole are around here, very close to the north. But what this diagram for Europe, the European community measured a north pole that was basically close to the equator in the Cambrian. And in the Carboniferous, it was there. And the Permian, it was there. And the Triassic, it was there. Okay. So the Europeans said, well, it looks like the magnetic north has moved. And then the North American paleomagnetic people made their measurements, and they said, well, no, we're seeing the North Pole for the Cambrian being here. And there's a big difference between our apparent polar wander curve and the European one. And they only come together now, right? This is Cretaceous. Capital K is used for Cretaceous. That's what, 100 million years ago or so? So the two communities fought about this. Oh, you don't know how to make measurements. They told each other. But then somebody realized, well, wait a minute. If we rotate the continents back the way that Wegener and Bullard wanted us to do it, these apparent polar wander curves line up with very few problems, right? This is what the apparent polar wander curves look like if we put Europe and North America together. They line up. So this is a very powerful argument in favor of continental drift. If we want, I mean, the Earth can't at the same time have two different magnetic poles. So either their measurements were wrong or there had to be something else going on. And so this paleomagnetic observation piled on top of these other lines of evidence that we've been discussing was very compelling. So there's two ways to display these apparent polar wander paths that your book shows. So here's one, which is the magnetic pole stays fixed and the continent moves. So this is South America. You know, this is where it is today. And so it could have done like that and left the magnetic pole in the, that's probably the South Pole. Or you could say, no, the continent stayed fixed. And what happened was the magnetic pole moved like this with time. Those are equally possible explanations. And so you have to have other data to choose between them. And you can see, given the discussion about continental drift, which ones the paleomagnetic community came down on. So recall this Bullard fit. This can be tested by paleomagnetics. So here we have an example. This is the apparent polar wander paths for Europe, which are the open circles, starting at 475 million years ago, up to 195 million years ago, Jurassic. And for North America, which are these solid dots, right? So there can't be two different poles. So the pole could have migrated like that, but it can't migrate. It can't possibly have migrated along both tracks. So when the paleomagnetic people took the Bullard fit and put it back together, they got this kind of an alignment. And there's always a little bit of slop in old data, right? There's still slop there, but you can see that this fit, especially for the last, say, 300 and 400 million years, is a much better one than this one where they're far separated. Yes, Clint.
And possibly no coincidence that around, well, particularly 370 to 345, they were getting united into Paleozoic Pangea.
Yes, a little bit younger, but yeah, the 300s. So this is the apparent polar wander path for Gondwana. So this is the Cambrian would be very close to the equator. It goes like that, and goes like that, goes like that, and like that. Ends up around there 65 million years ago at the beginning of the Cenozoic. So that is an interesting apparent polar wander curve, but it's much better explained as if the magnetic pole stays in the South Pole, North Pole area, and the continents move around. So these paleomagnetic arguments were incredibly powerful in convincing skeptics that Wegener was right. It was something he knew nothing about. The field of paleomagnetics just started evolving sort of after the Second World War. So here we've got, your book shows this example, and so what we can see is the interpretation of the magnetic pole staying fixed and the continent moving. And here we've got a continent staying fixed and the magnetic pole moving. So here we've got two continents, right? They're together, 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 together. They break up. One continent goes this way to the north. The other one goes to the south. Then they come back together, combine again at 12, right? So this could be one supercontinent. This could be the second one, right? And then they move together. And if you say, no, that didn't happen, the continents were always in their certain position, then what you have to do is something like this, that there are two magnetic poles, one for each continent, which is physically impossible. Earth's magnetic poles have always been a single one. Even if it wasn't a dipole, it was the same magnetic field for all of the continents in the Earth. And you have to do something like this, going, the poles separated. Like, you can't do that. So this kind of an argument convinced the paleomagnetic community and many people who were impressed by this independent line of evidence that Wegener really had it right for the most part.